Hello and happy Wednesday, guys! Again, I probably filmed this video the exact same day that I filmed yesterday's because I'm wearing the same outfit, in case you didn't notice. I try not to repeat my outfits within the same 2-week period, but it happens from time to time. Anyways, no shame. What we're going to take a look at today is slope triangles, and it's something that you dabbled with a little bit yesterday. If you remember, you did 214 and 213 in the ebook, or at least portions of it, as part of our Desmos activity, and you didn't even know it. Incredible, right? So anyways, the triangles in problems 2, 13, and 14 are called slope triangles. Handy new tool. Slope triangles. So go ahead and open up your notebook. Get to the sheet where you started taking notes yesterday, and then write down what slope triangles are. Okay? Now, slope is a measure of the steepness of a line, right? So a steep slope, if I'm going to go skiing down it, odds are that very, 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 very steep slope is going to have me going very fast because there's not a whole lot of horizontal distance. So I'm going to keep going faster and faster and faster, right? That'd be a fun hill to sled down, wouldn't it? I've never been skiing, so I'm going to stick away from the whole skiing thing because it's not really relevant to me. But anyways, if I had a not so steep slope, that would be like walking through the entry level of a wave pool. I don't know if you guys have been to like Kalahari or Zambezi Bay, or like the first bit of sand at the beach, or when you go to a lake. That's not very steep, is it? It slowly gets deeper and deeper as you ease your way in and kind of cool off, right? But anyways, it's definitely not something super steep that just shoots right up, is it? No. So anyways, slope is the measure of steepness of a line because we can quantify it, right? But anyways, it's the ratio of the vertical distance to the horizontal distance of a slope triangle. So the vertical part of the triangle is called delta y. Now that may be the nickname that I gave the Delta Chi's in college, but they seem to have a lot cooler events than I did. But anyways, delta y, which we'll read as change in y, it's the Greek letter delta, and then y, which we've always worked with, is change in y. Now the horizontal part of the triangle is called delta x, which is, we read it as the change in x. So delta y means the change in y, and delta x means the change in x, all right? Note that delta is the Greek letter delta, so eventually you guys may work with in engineering and calculus and physics alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, omicron, pi, rho, sigma, tau, upsilon, phi, chi, psi, omega. And what's a whole lot cooler is when I can say my alphabet backwards, like z, y, x, w, v, t, s, r, q, p, o, n, m, o, k, j, i, h, g, f, e, d, c, b, a. But anyways, this Greek letter delta is often used to represent a difference or a change. So delta y, the change in y, or the change on the vertical axis, and delta x, the change in x, or the change on the horizontal axis. So we're now going to explore it using our Desmos e-tool. So we see we have this graph right here. I'm going to go ahead and blow it up on the screen. And so now that we see that way up in our top corner, you can see that if we take a look at our graph, there's a change in x and a change in y that is labeled. And with the way that it's labeled on our graph, it kind of makes a triangle, doesn't it? Well, we want to know what the vertical distance or the change in y is, and then we want to know what the horizontal distance is. So first, let's look at the vertical change. If we go ahead and we take a look now, you'll see that if our starting value is where y is 2 on our line, and if we go to the corner of our slope triangle and we count up, we increase by 1 and then increase by 2. So our line grew from 2 to 4. That's a change in y of 2. So our delta y is 2. Now we want to find our change in x for this slope triangle. So if we take a look at our change in x, we went from 0, where our line crosses that y-axis, and if we go across that dotted line, we have 1, 2, 3, 4. So our change in x is 4. So delta y is 2, our change in y is 2, and delta x, or our change in x, is 4. So we're not going to find the graph on the resource page, and we're not going to draw smaller slope triangles, but now I want to write a couple of things down. So when we looked at our graph, and we had our line, we determined that delta x was equal to 4 and delta y was equal to 2. And from our original notes, we already know that our slope is a ratio of the change in y to the change in x. So again, the change in y to the change in x. So when we write that ratio in fractional form, we have delta y over delta x, or our vertical change over our horizontal change. So if I'm going to calculate my slope for this line using the slope triangle that was provided to us, and I'm going to put delta y over delta x, then I'm going to have 2 over 4. Now, I can simplify that pretty easily, and so my slope is 1/2. So it's positive, it's a positive slope, and we're growing, but what that means is every single time that we go up by 1, we're going over 2. So if we made some hypothetical grid lines, every single time I go up 1, I go over 2. And I go up 1, I'm going to go over 2. And so if we go ahead and we're going to go back to take a look. So again, taking a look at this graph, as I increase by 4, I go up by 2. So every time that my y value increases by 1, my x value increases by 2. My change in y is 1. My change in x is 2, which also goes along with the fact that my change in y overall for this slope triangle is 2, but my change in x was 4. So 2 over 4 and 1 over 2 hold the exact same equivalency. It's 1/2. And that is our slope. So now, if we're going to go ahead and write an equation for the line, we need to take a look at our starting point, right? So we have our slope, and we need to take a look at our starting point. And let's think of this in terms of the tile patterns that we've already tackled. When I have figure 0, I've got 2 tiles. When I'm at figure 2, I have 3 tiles. Figure 4, I have 4 tiles. So if my slope is 1/2, so each figure I'm adding half of a tile. I know we didn't deal with any half tiles, so it's kind of weird. But my starting value is 2, and I'm increasing. Every time y increases by 1, x increases by 2. And so if my slope is 1/2 and my starting value is 2, I have everything that I need to go ahead and write my equation. So when we come back over here, we have that our slope is 1/2, and so our equation is always in the form of y equals something. So I've got y equals, and remember, our slope is 1/2, so when our y value increases by 1, x increases by 2, and we had a starting value of 2. So again, if x is 0, then our y value is going to be 1/2 times 0 plus 2. Y is going to equal 2. And when our x value is 1, our y value is 2.5. And when our x value is 2, our y value is 3. And that lines up perfectly with the graph. So the equation for our line is right there.